Question number 30 from section 259, or section 6.2 with MA 259. First, I want to point out that numbers 19 through 28, which I don't believe I assigned you any of those to do, but they tell us that the critical point is 0, 0. And we use the same techniques that we used for the last problem and we're going to use for number 30, except for some of the work's already been done for us because they're telling us that the critical point is 0, 0. But what I'm more interested in us being able to do is finding the critical points on our own by taking the derivative set it equal to 0. The derivative's already been taken for us, of course, because it is a differential equation. Set that equal to 0. And then figuring out what the critical points are, and then at each of the critical points evaluating what is happening there. And so in the case of 29 through 32 in your book, that's what it's really asking you to do. Figure out what the critical point is on your own or multiple critical points, and then evaluating what's happening. So number 30, we have this differential equation, dx dt equals y minus 1, and dy dt equals x squared minus y. Now the first thing I want to point out that this is not a linear differential equation, right? This is something else. And so what we can do is use the Jacobian matrix technique to figure out what's happening around these critical points. Now I want to mention that analytically we may not be able to solve this differential equation. That may not be possible to do that in some analytic or closed form. However, we can still get a sense of what should be happening around the critical points. Okay, so what I did is take y minus 1 and set that equal to 0, and take x squared minus 1 and set that equal to 0. So from this first equation, y minus 1 equals 0, I get y equals 1. And when I plug in y equals 1 into the second equation, I get x squared minus 1 equals 0. And I solve that for x, I get x is equal to plus or minus 1. So that means I have two critical points. I have the critical point when x is equal to negative 1 and y is equal to 1. And I have the critical point where x is equal to positive 1 and y is equal to 1. So these are my two critical points. Okay, so then what I do is take the Jacobian of this system, and so this is equation 1 and this is equation 2. So I do equation 1 partial derivative with respect to x, and equation 1 partial derivative with respect to y, and equation 2 partial derivative with respect to x, and equation 2 partial derivative with respect to y. So equation 1 with respect to x is 0. Equation 1 with respect to y is 1. Equation 2 with respect to x is 2x, and equation 2 with respect to y is negative 1. So I have this Jacobian 0, 1, 2x minus 1. And so I plug in the Jacobian, my first critical point, minus 1, 1. And when I do that, I plug in negative 1 where I see x, and I plug in positive 1 where I see y, and I end up with 0, 1, minus 2, minus 1. So then I take the a minus lambda I of this Jacobian. So I get minus lambda, 1, minus 2, minus 1, minus lambda. Take its determinant, set it equal to 0. And when I do that, I end up getting lambda squared plus lambda plus 2 equals 0. And then I completed the square to solve this. You could complete the square to solve it. You could use quadratic formula to solve it. I'm pretty sure it's not easily factorable. And so when I completed the square to solve this, I end up getting the situation where lambda equals plus or minus root 7 2i minus a half. And so the a part of this is minus a half, the a part. A minus 1/2 is the a, plus or minus bi. So the a part of this is minus a half, and that's less than 0. So I look at my table, And for my complex numbers, I have these bottom three here. And it tells me what happens if A is less than 0. A is less than 0. Then I have a stable spiral point. Stable spiral point. And so that's what this is. At the critical point minus 1, 1, I have a stable spiral point. So I wanted to make mention too of a stable spiral point, and sometimes that gets called a sinking node or a sinking point. And the reason for that is this would be the point -1, 1. And when I look on my phase plane, it looks like I am spiraling in. So its stable spiral point is heading in. And it often gets called a sinking node because if you think of it as like it's sinking down the drain, so this is sinking down the drain of a sink, or it's going in, sinking in. If it was going out, it would be called an unstable spiral node, and that's often called a star node. So it's like a star starting at the point and going the other direction, so it's spiraling out, and that's often called a star node. So that'd be unstable spiral point. So stable spiral point is often referred to as a sinking node or a sink node. Okay, so I did the same thing with the Jacobian at the other critical point, 1, 1, that we found way back here, critical point 1, 1. So I plugged in the Jacobian of that critical point 1, 1, and I ended up getting 0, 1, 2, minus 1. So a minus lambda I, take its determinant, set it equal to 0, and I end up getting lambda equals 2 or lambda equals -1. So lambda 1 is equal to -1, and lambda 2 is equal to 2. And so I have the situation where 1 is negative and 1 is positive. And I look at my chart, and 1 is negative and 1 is positive, and that's called an unstable saddle point. So unstable saddle point.